Okay, adjacency matrices. Now, these are basically exactly the same as our root matrices that we did in the Year 11 course, with the exception of the treatment of loops. The word adjacent means next to, and what we're looking at here are how many edges are next to each vertex. So when we start talking about loops in this section, the loop is one edge, so there's one edge connected. Last year when we did this, what happened is we were talking about the number of roots, or the number of ways we could get from one node to another. So if we were looking at from D to D, I could go clockwise around from D to D to D, and that would count as one. Or I could have gone anti-clockwise, so that second direction counted as a second root, if you like, from D to D. So we used to count loops as two. However, in this course, it's the number of edges, and so it's a 1. That said, you need to read questions carefully, because if the context of the question was one where you are looking at the ways you can travel between things, and then you need to consider whether that's appropriate then to treat it like we did last year as a root matrix instead. But if the word says adjacency, it's how many edges are next to. So let's do one. So here we've got 4 vertices. So when we set up our matrix, we would have our rows and columns of the vertices that we have. And don't forget to read it the way you would any text, reading it from left to right. So starting from the left is our from, and we're going to the right as we move along. So my first cell here is going from A to A. So if I was to fill that in, from A to A there are no loops, so there's 0 ways that I can go from A to A. From A to B there's one edge, so I'd record that as a 1. From A to C there's one edge, so I'd record that as a 1. And from A to D there are no direct edges, so that would be a 0. If there were directions, if there were arrows on this, then that might change things as well. But at the moment we've just got the edges, so we will just record those. The second line, from B to A there is only one line, so we've got a 1 there. From B to B there are no loops, so there's no ways I can do that. From B to C there's one line, and from B to D there aren't any lines, so I'd have a 0. From C to A there is one line. From C to B there is one line. From C to C there are no loops, so that would be a 0. And from C to D I've got one line. Finally, from D to A there are no lines. D to B there are no lines. D to C there's 1. And D to D there is that one loop, and as I said before, that would count as a 1 in the context of an adjacency matrix. Now your textbook does talk about matrices to powers. So if I call this whole matrix we normally give it a line, let's call it matrix M. So if I call this matrix M, if I raised it to a power, so if I said M squared, hopefully you remember from last year that if I talked about a power of 2, it means I've gone along 2 edges. So if I was saying from A to A, if I was redoing this as a squared matrix, starting from A, I can go to B and back. So that's used 2 edges. I'm basically going there using the same edge to come back. So that would be one way. Or I can go to C and then back. That would be a second way. So from A to A, in that case, I would have a 2. Now, however, this course, it's kind of out of the scope of this course. They don't really talk about those things in this course. Your book has covered it, and it wouldn't hurt to have it in the back of your mind as it is possibly presumed knowledge. But really, we don't cover that. Just to revise you, if I had an m to the power of 3, it would mean that I've travelled along 3 edges or via 2 other vertices. So again, if I was saying from A to A, I've got to use 3 edges, so there'd be one way I can go 1, 2, 3, or likewise I could be going back in that same direction, 1, 2, 3, and back again. And I don't see any off the top of my head otherwise. Remember from last year though, if you did have to do that, the easiest way to achieve it is to put your direct root matrix in, and then to just raise that to a power on your class pad. If I was to then give you an interpretation question, like I might say, what's that root matrix plus m squared plus m to the power of 3, the answer to that would be telling me how many roots of length 1, or length 2, or length 3. So as soon as I'm adding, I'm not, I'm just getting how many ways of each of those I could get. Shouldn't really be in this course, but just in case, that would be your reminder. I wouldn't stress out about that. Okay, now drawing graphs is another thing that we need to be able to do. When we draw graphs, basically I can redraw a graph any way I like, but so visually it can look like anything. But what I need to make sure I do is that I maintain all connections. So for example, if I looked at this graph, oopsies, did not mean to do that, sorry. A is currently connected to B and it's connected to D. So if I was to redraw this graph, I can redraw it however I like. I could literally put, so if I called that A, I could put B over here. I can put C over here and I can put D over here, let's say. A and B were connected, so A and B still need to be connected. A and D were connected, so A and D still need to be connected if I was to redraw this. If I then wanted to draw, fill in the rest of it, B and C are connected, so I would need to make sure that B and C are still connected. I've drawn that around the outside this time, and I'll talk about that in a moment. B is also connected, so B and C is connected. B is also connected to D, so I would put another line in there. Looking at C, C is connected to B and C is connected to D. I've already got the connection to B, but I would need to connect it to D as well. And then looking at D, I should have 3 lines coming out of D, which I currently already do. And D was connected, and I'll just put a highlighter on so you can see that. So D was connected to C, which I've already got. D was connected to A, which I've already got. And D was connected to C, which I already have. So you can see there that the diagram looks different, but in fact it's exactly the same because I have all the same vertices, I have the same number of edges, and they're all connected to the same vertices. So I haven't changed what's connected to what. Now, generally speaking, the reason I'm going to do this is to make a graph planar, and we haven't talked about that yet, but a graph is basically planar if none of the edges cross. Planar means flat. So if you can imagine that these were like water pipes, then basically as soon as they cross, it's no longer flat. However, if they ask you if a network is planar, then your answer must be yes if it can be redrawn to make it planar. So in this case, basically, by picking up one of these lines that's crossing and redrawing it however I like, but so that it no longer crosses, I can make it planar, and therefore the network will be considered to be planar. Down the track, we're going to be using a little formula called Euler's formula. And in that one, sorry, I just deleted one of your lines that I shouldn't have. And in that formula, we'll be proving whether or not things are planar. And before we use it, we'll need to redraw it. So here it is here. I'm just going to fix this line again, sorry. So Euler's rule is basically vertices plus faces, take away the number of edges, must equal 2. And what that proves by using Euler's rule, it proves whether or not a graph is planar. So I'll just write that here. So it proves a graph is planar, which means flat. Okay, so here I had 4 vertices, plus you can see I actually have 3 faces. So if I'm looking up here, I've got the one face here, I've got the one face in here, and then I've got the outside face as well. So there were 3 faces, and I might first undo all my little squiggles. So 3 faces, and edges, I've got 1, 2, 3, 4, 5, 1, 2, 3, 4, 5 edges. And I want to show that that's going to equal 2. So when you show your working, show your substitution in. There's generally marks they want to see what you've identified as vertices, faces and edges to make sure you can do that. And you can see here that if I was to do the maths, 4 plus 3 is equal to 7. Take away 5 is indeed equal to 2. So I'm going to wind up with a final answer of 2 is equal to 2, which is correct. And I would show that in my working, and don't forget to actually answer the question. And I'd say, therefore, the graph is planar. So I'd show Euler's rule, I'd show my substitution into that rule, and I'd say, therefore, yes, it is. Now, if I'd accidentally used the graph that hadn't been redrawn and I was trying to prove whether that was planar, and I'll just change colours here. If I tried to substitute into here, so vertices plus faces, take edges, still needs to equal to 2. If I didn't redraw, I might be tempted to go, well, there's 1, 2, 3, 4 faces, including the outside. My vertices would still be the 4, A, B, C, D. take away my edges, which is still my 1, 2, 3, 4, 5 edges altogether, has to equal 2. So at the moment, 4 plus 4 is 8. Take away 5 would be equal to 3. So 3 is not equal to 2, so you'd be showing it like that. And then you'd be saying, well, therefore, it's not planar. However, that would be incorrect in this case. So I'm just going to sort of circle that and show that we would not do that. So that would be how I'm going to show it if it was legitimate. Oh, and I've put a, my bad. Sorry, not equal to 2. But we would be saying we're not going to use that because we could redraw it. And if I can redraw it, I should do so. But if there was a legitimate one where it couldn't be redrawn, then that's the way you would show your working to prove that it was in fact planar. Now, some more terminology that we need. Simple graphs, before I move on, Euler's rule, because this does come into a lot of our course, Euler's rule is used to show that it's planar, but it's also used at times to find the number of vertices or the number of faces or edges. So at times they'll give you questions where they tell you you've got a planar graph, and they'll tell you how many, they won't show it, but they'll tell you how many edges or faces or vertices and faces or whatever. They'll show you 2 of those 3 things, and they'll ask you how many of the missing one we must have. And if then, of course, you're just going to use algebra, you're going to plug into that rule and find the thing that you're missing. Okay, simple graphs. So simple graphs are the ones that have no loops and no multiple edges. Generally speaking, they tend to also have no weights and no directions, but we can have a simple weighted graph or a simple directed graph. So overall, it's only simple if it has no loops and no multiple edges. A connected graph is, as the name implies, one where all the vertices are connected. So that means that they're attached by edges. So a path exists between all the vertices. Doesn't need to be a direct path, but I can get from one vertex to another, any other one, by following some edges. Now, this brings me to the point of bridges. So bridges are edges which, if removed, would leave the graph disconnected. So if I tap on my little eraser here, you can see that C to D would be a bridge. Because if I removed that edge, you can now see that my graph has 2 sections and they're not connected at all. So I now could no longer get from D back to A, B or C, and I couldn't get from E back to A, B or C. So that would be a disconnected graph at this point, and CD for that reason is what we call a bridge. So I'll put CD back in. And likewise DE is a bridge, because if I took away DE, then that would leave that little loop disconnected, and it would again be a disconnected graph. So D to E, that edge, is also what we call a bridge. Disconnected graph is one like we showed above, where the 2 parts, it can be more than 2 parts, but parts of the graph are not connected to other parts of the graph with an edge. So here I've actually drawn this twice, but it's the same diagram. So I've got a graph here which has 3 edges. It has the 1, 2, 3, 4, 5 vertices, but they're not all connected to each other, so it's a disconnected graph. At times they'll try and trick you by redrawing it, so that's the same graph redrawn here, exactly the same one, and all I've done is redrawn it so that the lines overlap. But these overlapped areas do not have a node at them, so they're not connected, and I can redraw that so it looks completely disconnected, but regardless of whether I do or not, that would be a disconnected graph. But don't forget that at times they will try and trick you, so just keep an eye out for those. Directed graphs are those that have directed edges, which basically just means that there's little arrows which show you which way you can travel. So that would be a directed graph. Complete graphs are graphs where every vertex is attached to every other vertex. And we use a capital K to denote that it is a complete graph. And the little subscript N here shows me how many vertices it's got. So if I was looking at the graph below, I've got 1, 2, 3, 4, 5 vertices. So I'd say that this is a K5. For any complete graph with N vertices, we know that it will have N outside of N tape 1 over 2 edges. So at times you'll need to use that little fact. Weighted graphs are graphs where the edges have weights, that is numbers written on them, and those numbers represent distances or costs or something to do with the context of that question. bipartite graphs are another important concept. These are basically graphs where the vertices can be split into two different vertex sets. You can think of them almost like teams, but don't use that language. They're very particular about the language, so we'll call them a vertex set or a vertex group. Now, each vertex, a vertex from any one group can be joined to one or more vertices in the other group, but vertices within a given group or a given set will never join to each other. So the example I've given you here is a set of students and what subjects they study. So I've got Joe, Ben and Kel, and at the bottom I've got their subjects, maths, English and biology. So you can see here that Joe does maths and English, Ben does maths and biology, and Kel just does biology. And so that the students never link to each other and the subjects never link to each other, but the students, and that would make sense, link up to the particular subjects. Now, a complete bipartite graph is a bipartite graph where each of the vertices, again, in one set are connected to each of the vertices in the other. So here, basically, I would need to connect Joe up to biology to complete that one. If I connected Ben up to English so that he's got all three, and I'd connect up Kel to the English and also to the maths to complete that. And so you'd wind up in a complete graph with every vertex in one set connected to every vertex in the second set. But again, vertices within a given set do not connect to each other. Now, I'm just going to undo those there. Okay. The complement of a bipartite graph is the only other thing that you might need to know about those. And basically, they're the edges that you would need to add to the graph to make it complete. So that's exactly what I just did with the highlighter a moment ago, and I'll change colours and do that again now. So to make this graph complete, I would need to connect Joe up to biology, and then Joe's connected to all three. Ben was currently only connected to two subjects, so I'd connect him to the third. And Kel would also need to connect to all three, so I'd put in his two extra edges. So the green lines there would be the complement of the original graph. They make it complete. Okay, now testing if a graph is bipartite. Now, often they'll give you a graph. It doesn't look bipartite in that it's not obviously set up with my two sort of distinguished sets looking obvious. So they might give you a random graph, but they'll ask you, well, is it bipartite? And you need to do the check based on that definition. So we know that in order to be bipartite, a vertex can't be connected to another vertex in the same set. So if I made my way around this picture, starting with A, what I know about A so far is that they've connected it to E and B. So if this was bipartite, then E and B would need to be in the other set. Okay, and then they would be connected like so. If I then went to B, so I'll change colours here. If I then started from B, what I know about B is that if this was bipartite, then it shouldn't be in the same team as A, D or C. So wherever B is, and B I already had here, it would mean that A, C and D must be on the other team. And so far, that works out all right for us. Now we'll change colours again. Then I'll check my next one, so C. If this is bipartite, then whatever team C's in, and C's currently at the top, then I know that the ones it's connected to must be in the opposite one. So it's connected to G. So I'd know that G would have to be on the other team, and that's okay so far. B would have to be on the opposite team, and so far that's fine, that's already there. And E, so hang on, E, G, and B, and they're all on the other team, so far so good. Then we check G. So wherever G is, G's on the bottom team at the moment. We would know, or set, I should use the word set. So G is connected to C and F. So C and F would have to be on the other team. We don't have F, so I'll put that F there. Okay, then we'll check F. So wherever F is, F's up the top. F can't connect to E or G. And again, that's so far fine. E and G are both in the bottom one. Now we'll check E. So E is on our bottom team at the moment. It can't connect to D, that's at the top. C, that's at the top. D, C, G is in the bottom. So E and G. Oh, sorry, I've not got distracted by that noise in the background.